Hey, this is a short video on the ideal gas law, which you guys have probably used before. So if we're at STP, we already said that if we're at STP, 1 mole of any gas, doesn't matter what gas it is, 1 mole of any gas at STP takes up 22.4 liters of space. So at STP, 1 mole of gas would fit in this box. Doesn't matter if it's oxygen, nitrogen, carbon dioxide, 6.02 times 10 to the 23rd molecules would take up this much space at STP. If you have double that many molecules, take up double that space. So whenever we're at STP, I just use that. Okay. Use the ideal gas line when we're not at STP. So let's look at this ratio. We said this ratio never changes. Okay. This ratio is always the same answer. Okay. And it always equals R, the ideal gas constant. So let's think about this. If we have 1 mole of gas, so I'll put 1 mole in there. If we have 1 mole of gas at STP, so at 273 degrees Kelvin, and a pressure of 1 atmosphere. So you got 1 mole of gas at 1 atmosphere, 273 Kelvin. It takes up 22.4 liters of space. So plug in a 22.4 for volume. There's our pressure, volume, moles, temperature. If you put those in there, you get an answer of 0.0821, 0.08205, but we'll just say 0.0821. Your label's weird. It's atmospheres times liters per mole per Kelvin. There are different ones. We'll pretty much stick with that one most of the time. So this ratio always equals 0.0821. Doesn't matter if I plug in this. This is way less than 22.4 liters. So that's going to be a small number. But this is also small. We're not at STP, we're at a higher temperature. We're also a little bit lower pressure. If we plug in the conditions of this gas, its volume, its moles, its temperature, its pressure, plug those into this, we'll get 0.0821 for an answer. So whenever we have a gas not at STP, we can plug into this and figure out other things about it. Now usually we'll be solving for volume or moles. Okay, these problems have a little bit more, but almost always we'll be solving for volume or moles. Now I don't like to solve it written like that, so we write it as PIV-NERT. PV equals nRT. Okay, PV equals nRT is a much easier way to solve it. So remember, this has to be in moles. R is 0.0821. That's got to be in Kelvin. This has got to be in liters because of our R value. And pressure has to be in atmospheres. So we got to make sure we have all those things in the correct thing. So this one, we got 3 grams of a gas. Remember, 3 grams is not going there anywhere. Moles goes in here, so it's turned into moles. 5 liters can go in for volume. 92 degrees Celsius, change into Kelvin, so plus 273, which would be 369 degrees Kelvin, 365 degrees Kelvin, sorry. It's saying what is the pressure in the container. So plug our numbers in. PV equals nRT. We know we're looking for pressure. The volume is 5 liters. Our moles, we have 3 grams of SF6. SF6 is 146 grams per mole, so 3 grams, 146 grams per mole. So we can divide those and get the number of moles. I'm just going to plug in 3 over 146 as our number of moles, whatever that answer is. R is 0.0821, and our temperature is 365 degrees Kelvin. That's a pretty small number of moles. Okay, pretty small number of moles. So our pressure is probably pretty low. Multiply these 3, divide by 5. It's a 5, not an S. And we get a pressure of 0.123 atmospheres. Pretty low pressure because it's a pretty low number of moles. The more moles in the container, the more pressure. You know, if I shove more moles of gas into this container, it's going to cause more pressure unless I change the temperature or volume with it. I'm going to go down and do one of the ones towards the bottom. So I'm going to do letter D. So PV equals nRT. Again, we use this when we're not at STP. We have different conditions, trying to figure something out. There's our grams of a gas. Notice it doesn't tell us what gas it is. Okay, so we can't get moles. Cannot get moles. We don't know what gas it is. Volume would be 0.226 liters. Very, very small volume. Okay, be smaller than this gas. 749 millimeters of mercury. That's the pressure. We need to take 749 divided by 760 because 760 millimeters is how many millimeters of mercury are in 1 atmosphere. And temperature plus 273 is 285 Kelvin. So plug it in here. Pressure is 749 over 760, which is basically like 0.98 or something like that. Volume is 0.226 liters. I don't know what moles are. R is 0.0821, always, unless we have different labels. And our temperature is 285 Kelvin. Sorry about the glare on the screen, so you can't see that. So I'm going to solve for moles. It gives us grams. Okay, it's asking what is the molar mass of the gas. So before we solve, think about what molar mass is. Molar mass is the number of grams in 1 mole. Well, if we figure out how many moles we have, we can set up a proportion and go, we have this many grams making up this many moles, so we can figure out how many grams are in 1 mole then. So if I multiply these, divide by these two, I get moles of 0.009525. That's a very small amount of moles because we had a very small container. So this many grams make up this many moles. So I can set up a little proportion and go, well, if 1.973 grams is 0.009525 moles, then how many grams are in 1 mole? So I'm really just taking this divided by this to figure out how many grams per mole it is. And you get about 207.3 if I divide those two. So that is the molar mass of that gas. I'll let you guys finish up the other problems.